Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm your host, Kristin Malavenda, the Communications Director for the department. In each episode of Engineering Innovations, I sit down with faculty from Purdue ECE to talk about their path to becoming an engineer, the focus of their research, and the future of the field. Our guest today is Alexandra Boltasseva, the Ron and Dotty Garvin Tonjes Distinguished Professor of Electrical and Computer Engineering. Thanks so much for joining me today.
Thank you so much, Kristin, for having me here.
We're going to start with the basics. What led you to electrical and computer engineering? Can you remember the earliest memory of what would have turned into being a good engineer?
Yeah, it's going to be a long story.
All right.
If I start from the very beginning, but to tell you the truth, I never thought that I will be an engineer. And the answer to that is also related to the fact that engineer in Russian or back in the Soviet culture means something else. Here, when I am engineer and I'm engineering professor, but what it would correspond to in the Soviet system would be actually applied physics and devices. And an engineer, if you think in the terms of the Soviet system, would be more of a technician, I would say. But nonetheless, I think that it's not that I was dreaming about becoming a physicist from the very start or being an engineer or dealing with devices. But I grew up in a family of engineers.
Oh, there you go.
So in this way, I was kind of destined to be in STEM. I think that was pretty clear. Now, my dad was an electronics engineer.
Okay.
So he worked for a railroad system. And in fact, it's interesting because he was securing safe communication because the little town where I was born is on a southern part of the famous Trans-Siberian route.
Okay. Yep.
So he was kind of servicing, and the unit he led was servicing and making sure the communication is secure all the way from one big city to the other.
Gotcha.
And my mom was trained as in math from mathematical department and in applied math, and she was working with the very first computers.
Wow.
So I grew up with the punch cards all around.
Wow, that's amazing.
Yeah. But when I remember myself in the childhood, I was just, I was just curious about everything around me. And this curiosity is just simply because I had such amazing parents and grandparents. I remember long walks with my dad, and we lived in a small town, so we usually would, go somewhere in the forest to pick up berries and mushrooms. Really luxury, I understand now.
Yep.
With wild strawberries and my dad would always, tell me all kinds of stories about Big Bang and multiple universes and all this fascinating things and unexplained natural phenomena.
Okay.
So I was very curious, and so I read lots of books. And again, I think I should thank my family, obviously, but also a little bit of this really Soviet system of education.
Okay.
Where in the image in the society of a physicist or engineer was so high, and there were books and movies, and the hero in the movie was a physicist.
Interesting.
It's not a finance person or entrepreneur. It was a physicist.
Yes.
So I kind of grew up in that, but I wanted to be working in biology.
Okay.
And my dad would always say, well, when I retire, I become a forester. I would work in a forest where your research institute is, and you will be studying whatever animals or plants. And then it just happened so. So back to your question, why and how I became an engineer, I would say, well, this is just a row of events and amazing people starting from my family. And the next really pivotal point was my physics teacher in middle school.
Okay.
So he changed my way of thinking about biology, physics, and everything. And I started after school classes in physics with him. And he was the one who told me that I should go study in in the best technical institute in the Moscow Institute of Physics and Technology. And he prepared me well for that. And I'm ever so grateful because I loved physics. I loved the way he taught. I started to participate in like regional and also Russian level Olympics in physics. And I just loved it.
Yeah.
But I loved it because of him.
Okay.
So
yeah.
he was an amazing teacher. And as I said, it just happened so that I ended up in what's called the Russian MIT, Moscow Institute of Physics and Technology. And we say Russian MIT because indeed, from now American point of view, it is preparing engineers. But my degree, if you look at it, would be in applied physics, so math. So that's where the difference is coming. Yeah. It's really coming from. And then again, the way I ended up in engineering and not in physics was also kind of, I wouldn't say accidental, but just because I made the right people in the right time. So when I was studying in PhysTech, that's the name of the MIPT.
Okay.
I actually originally was mostly fascinated about high-energy physics and elementary particles.
Okay.
And in this country, it's not engineering, right? That would be a physics department.
Yeah.
But I studied there during really hard times. It was after the crash of Soviet Union. It was the 90s where everything collapsed.
Yeah.
And there were no money for fundamental science. And the institute that I was supposed to do my diploma in and do research in this elementary particles and other things were kind of really silent. And a lot of people left for West already.
Okay.
A lot of scientists left, and it was kind of dusty and very spooky.
Yeah.
And again, it just happened so that the head of department at some point, he talked to me and he said, Sasha, why don't you try for this semester? If you don't like, your research at this institute, why don't you try something else? We have a really nice small lab here on campus that's working with semiconductor lasers.
Okay.
And why don't you go there? And I know the PI, and you can just go there and do research for this semester with them.
Yep.
And it's just worked out. I thought that apparently I really love doing something where I can, touch things.
Mm-hmm.
I can put them and measure and kind of see what you're doing.
As opposed to
As opposed to, finding a Higgs boson. Well, I know they finally found it, but it took a long time and many people. And that's how I stayed. And I did my diploma with semiconductor quantum well lasers. Again, ever so grateful to my advisors in the Lebedev Physical Institute. And then I applied for PhD in Denmark, already in a slightly different area, but still it was like optical technologies and photonic crystals. So again, if I look back, maybe it would be a different teacher.
Yeah.
I would be in biology, right? In the science department, striving and enjoying. That's kind of a path. So, which I want to make an interesting point here. I think it's interesting because people very often talk about passion.
Yes.
Yeah, I was so passionate about engineering from when I was like 5 years old.
Right.
And at least for me, and I think for many people, it is not about passion. It is about being good at something and really starting to enjoy. And I made a discovery recently. I read a book that's called So Good They Can't Ignore You, which talks about that. Yeah. And I think I'm going to give it to my kids because it really says that there are so many pathways that we can pursue. And it's hard to choose.
Right.
And you don't know sometimes what your passion is. Am I going to be a successful engineer? Or then it's just a matter of starting something, being good at it, and then figuring things out.
Yeah.
You also need some luck, and you need to meet the right people to help you. And I'm ever so grateful to all the mentors and teachers that I had. I'm here because of all of them.
Yeah. So you're talking about, find something you're good at, and then you develop a passion from then. I think that's a good point because I think there's a lot of pressure, especially in the United States, for like 17 and 18-year-olds to know what they're going to do for the rest of their lives. And I think it can be overwhelming.
It is. And I think it can be overwhelming. I can, lead to anxiety. Oh my God, I have a friend and she's like dancing since she was 3 years old. And
Right.
and what I'm good at, and I always say, and actually sometimes we discuss it in family, that, you just have to be good professionally in whatever you're doing.
Right.
And if you become so good that they can't ignore you,
Yeah.
then you start enjoy it because you will be working at the capacity where people ask your advice,
Right.
where you understand things so deeply that you can start making connections to other areas as well.
Right.
So in this way, switching from being a really, really high-level professional in one area to being a professional in something else is much easier.
Gotcha.
But you have to be good at it.
Yeah, and you have to work hard no matter what you're doing. So
that's for sure.
So do you see any engineering sparks in your children?
Yes, definitely. Definitely. And really engineering sparks. I wouldn't say that I had those, but if I talk about my older daughter, she's a junior at ACE at Purdue right now.
There you go.
I remember her building all kinds of weird stuff from a very young age. You give her a piece of paper and you would expect her to draw something. And then she suddenly comes and she made a brush where she used scissors and glue and she made something out of it.
Right.
Or she would play with a teddy bear, and instead of just playing with a teddy bear as other kids do, she would construct a vehicle for the teddy bear. And, or something where water would run. And I was like, okay, she is going to be an artist or an engineer.
Right.
But for artists, I don't want her to be an artist because, you have to have a stable profession. That definitely.
So you could tell from a young age that she kind of saw things differently than maybe an average toddler or young kid did.
Absolutely. Yeah. And also in the level of curiosity for how things work was always amazing.
Yeah.
I mean, we board the airplane and then she's like, what is this small thing doing? And I should ask the flight attendant. And by now she knows like all types of airplanes. She knows exactly where things are and what this beep means. And again, just because it's interesting for her how things work.
Yeah, that's amazing. So let's venture into your type of engineering, your research, which I'm going to be perfectly honest, I don't always understand what it is. And you'll send me something and I'll think, and then I'll get the abstract and I'll think, So explain to us about quantum photonics, nanophotonics, those kind of things, and where someone would understand how that impacts the real world.
Yep. Actually, I'm going to start with my dad again.
Okay.
Because, as I said, he was an electronics engineer. So he was working on communication systems using, very old-fashioned cables and communication based on electronics. And what he says very often is that I retired him because by the time he was ready to be retired, optical fibers came in.
Okay.
And the optical fibers, obviously, they change the way we live.
Right.
We communicate and, all the internet and cross-Atlantic cables. And so the world will be very, very different without advances in optical technologies. Broadly, optical technologies and everything we can do with light and photons running down the cable, the optical cable or optical waveguide, is what I am interested in.
Okay.
And obviously, when we talk about optical technologies, then we can think and look around us and find many, many technologies that are actually using light. So I just mentioned the communication system. It's undeniable how the world has changed with that. But also the way we use optical sensors, and we use a lot of optical technologies in medicine. Just think about all these revolutions brought with lasers, and as a surgical tool, as a tool to fix the vision, and and for environmental purposes and for energy conversion.
Right.
And for quantum. Quantum is a buzzword. It's everywhere. And every time people say quantum, they kind of think about quantum computing, right? Which is kind of still elusive. With that said, we do have very powerful quantum solvers. We don't have universal quantum computer yet.
Okay.
But we have very powerful machines already now that are able to solve very complex problems in a, let's say, faster or more straightforward way that we could do with classical computers. And quantum is not only quantum computers.
Okay.
Quantum is also quantum sensing and quantum communication. So it's like 3 pillars of quantum.
Okay.
And in all 3 pillars, there is a very big promise for using light, right? So you can use light for, well, obviously you can use optical communication systems. Future quantum communication system will be utilizing light. And hopefully we can leverage the same infrastructure that we have for optical fibers right now. We just have to figure out how to send quantum light in the fibers and how to preserve its properties and to make it more secure. Quantum sensing is the same thing. Using quantum light, you can actually have much higher resolution, and you can develop sensors that can outperform anything that you can think about in the classical way. And quantum computers can also be realized using photons. So all this aspects of technologies and science that you can do with light broadly is of interest to our team. And I say our team because we are a large team of people really passionate about nanophotonics, quantum photonics at Berkeley National Center. And it's we kind of co-lead it with Vlad Chalayev and Alex Kildashev, other 2 great professors of ECE. The 3 of us, and together with our senior research scientist, Alex Laguchuk, we co-advise our students and postdocs and work as a team. So making light work at nanoscale is the other way to put it in terms of my research. So we want to make sure that we can scale down the optical components. We want to develop all kinds of interesting devices that we can integrate onto the single chip to boost the functionality, to introduce different functionalities into the single chip. Just to give you an example, most recent advances of the Berkeley team in nanophotonics is the discovery of so-called quantum emitters. And one of the most promising technologically relevant platforms, it's called silicon nitride material. So it's we know that all the consumer electronic is silicon. Silicon nitride holds a promise as a platform for quantum on-chip circuitry. And structures that can emit quantum light, or let's say single photons, in this material are of huge interest to us. So we're trying to find ways to control it, to make single photon sources, to potentially realize, entanglement, and use it for communication systems and for quantum computing in the future. So there's just one example, but we're also interested in designing nanostructured, ultra-thin, kind of monolayers of optical materials that we can use for sensors, for energy conversion. We are very much interested in discovering new materials that we can use with optical devices. And in fact, discovering new optical materials is and has been a focus of my research and my team's research.
And so that you're looking for materials that make it more efficient and like less loss of the light or whatever as you use it?
Yes, absolutely. So that was kind of our first starting point, to look into better materials with less absorption. But, the interesting thing, what it turned out that when we look into new materials, they just bring so much more. They can also bring unexpected new effects and unlock new physics. Like we started to look at ceramic plasmonic materials, the ones that are made utilizing high temperature processes, because they're very durable and robust for high temperature applications. And they turned out to be very tailorable, so you can change their properties. You can dynamically tune them, so you can make tunable devices. And also, they opened up new chapters of physics for us. We realized, for example, that if we go to extremely thin layers of these materials, maybe 5-10 atomic layers, you can unlock interesting physical effects with how electrons behave, for example. And another way, another example of material is that we also, motivated by low loss and low absorption, we started to work with doped oxides in optics. And we found out that in addition to low loss, they offer some fascinating optical properties. So, for example, they offer a behavior that you cannot achieve with other materials, and namely that their refractive index is close to 0.
Okay.
That's something very peculiar in optic. And that's kind of back to our being good at something, right?
Right.
You start with a simple thing. Let's say you want to just find a new material with a better loss factor. But then you start digging into that and you start investigating and you realize that it just brings so much more, and you can build on that and you can utilize new effects to build a device with different functionality.
So your research leads you to other research.
By all means. We kind of started new directions based on what we have found with our original ideas.
So is physics the most natural kind of interdisciplinary partnership you would have? Are there other fields that are natural fits with what you're doing?
Well, physics, obviously, and as I said, but like most of what we are doing is engineering and applied physics kind of together, like seamlessly together. Material science is really big thing. And well, in fact, when I give lectures and I travel with more than like 15 years of experience with optical materials, people think that we are doing material science, and so material science is very important. Computational physics, so computation and is very important. So all my students are being trained in like numerical simulations and computational tools as well. Alex Kildashev is the one who leads computational efforts in nanophotonics at Berkeley, and computation then also is interface or leads to big data, AI, and machine learning.
Right.
And in fact, this research initiative, the Elmore Center on Quantum, Crossroads of Quantum and AI, does exactly that. So we're trying to leverage advances in machine learning, in classical machine learning, to use these advances to develop more efficient devices for quantum circuitry. And kind of it can also go the other way, right? You can utilize quantum hardware to actually do new types of computation. It's quite interdisciplinary. And if you think about sensor applications, then obviously chemistry, biology, and medicine to some extent can also be part of it, because we are interacting with people in those areas for sensor applications as well.
We mentioned briefly a couple of times Berkeley Nanotechnology Center. What's special or unique about that center? Is it the people, or is the facilities, or both?
Both. And what's most important is that Berkeley was built as this kind of synergy point. It has a shared facility, which is state-of-the-art and which is really needed. Like, all our students are based in Berkeley simply because all our materials and the structures that we make require this complex nanofabrication tools, but also because faculties with different backgrounds and from different departments are brought together.
Oh, that's interesting.
Yeah. So, and in fact, just when that's how I started optical materials. When I joined Purdue, I was doing like on-chip nanophotonic circuitry.
Okay.
And my interactions in Berkeley, actually with our former director and acting president, Tim Sands, led us to explore some of the interesting materials that are used for thermoelectric applications for optical needs. And that's led to new directions in research. So Berkeley really fosters this multidisciplinary collaborations and new ideas, because especially from students,
right?
You can chat in the hallways, but I noticed that good ideas and collaborations come very often from students. So they do some fabrication, they chat with students from other teams, and they start to and they just figure things out, how to help each other, but also to get inspired. So that's kind of a point of interfacing different disciplines, different approaches is what makes Berk really unique. So we enjoy this atmosphere.
Do your students, do you find yourself sometimes being surprised or amazed at what they come up with because they're coming from a different perspective?
Yes, and we would love to have more of that. We always say that, well, surprise us.
Yeah.
And that's exactly what we say, surprise us. And the way Vlad and I kind of operate our big team is we encourage them to think. And we travel a lot, and we always discuss different new ideas. And sometimes we just come after a conference and we say, hey, on the way back, we were just discussing what if we kind of take this material and look into this and that and those, and why don't you try to think what kind of interesting phenomena we can observe in these materials and what kind of devices it can be used for. And we task our students and postdocs who some more like senior have more experience, and then like in a week we will have a brainstorming session, and they will present few slides with some crazy ideas, and we kind of down select, and that's the best part. And that's the really best part. And since we have students and postdocs coming also from, as you said, different approaches and different disciplines, that really makes it unique. My first two students here at Purdue were actually trained in solid state semiconductor and then materials that I was never trained in.
Oh, wow.
So I learned a lot from them in terms of optical materials. Actually, my very first student, Guru Naik, now a professor at Rice University. And again, I learned a lot, and we started this area, and we want our students to be better than us from the very beginning.
Yeah. Well, when you're looking for students to join your research group, what qualities do you look for in a student that you think this will be a good addition to our group?
Enthusiasm, creativity, and it's kind of it is a fine balance between being technically good and the ability to see the big picture.
Mm-hmm.
Sometimes you have really, really qualified person doing extremely challenging technical tasks. But then if you ask questions and kind of touches upon what for and what's beyond, you see that, okay, he or she was just been doing this little part, been doing it good, but and then there are other type of students, the ones that are really curious about everything, but starting with the nature of photon, and they then they kind of start to be a little bit kind of dispersed everywhere, and they want to see this and that, and they tried a little bit of this and a little bit of that. So it has to be a balance. And as I said in the beginning, you have to be good in what you're doing, but you also have to have a really kind of high levels of enthusiasm, commitment, energy, and just excitement.
Yeah.
Because without excitement,
what's the point?
Yeah, what's the point? Vlad always says that if you're not interested in putting your PhD in the books for next generation, it's not worth it. So whatever we do has to go into textbooks.
Gotcha.
It's not always like that, but at least we should aim high. And this is something we also expect kind of our students to understand, that we can do, improvements, optimization, but that's going to be incremental work, and we want something big.
So as you're working with your students, and the nature of research is that it doesn't work out probably more than it does work out, when you reach roadblocks in research, how do you handle those, and how do you teach your students how to handle those?
Yeah. So it's a very good question. And in fact, it also depends on how the entire kind of research is built in the team. So our team is built in a different way and compared to maybe most of the teams, where each student has his or her own project.
Okay.
So we inherited kind of an old Soviet system, I would say, scientific system, where we work as a big team. And what it means is that, each student still has his or her own project, but we get other people involved in all the challenging parts.
Okay.
And the reason for that is very simple, because as I said, we aim high, so all our projects are very challenging, and every step is challenging. You have to come up with an interesting, new, fascinating design, right? It requires numerical simulations so that you can actually do that. For numerical simulations, you first have to feed the optical data into the simulation. So you have to grow and measure your materials, the material's optical response, the dielectric permittivity. So you have to have people who are really trained in how to make best materials, best performing materials. And then when you do the numerical simulation, you have to fabricate it. Nanofabrication is an art in itself.
Yeah.
There are some people that are not allowed to enter clean room, but and some of them that do magic, right? And the optical characterization part is also, sometimes you need, very complex nonlinear measurements. Sometimes you have to conduct quantum optical measurements that are very challenging. And along this road, if you just one-on-one in this, with these research tasks, you will not succeed very quickly, and you will not be able to achieve results as the best experts can provide in the team. So that's why we are, again, trying to leverage the expertise of other team members. Let's say we have a couple of people that are really focusing on numerical simulations. So whoever needs help or with his or her simulations would go to them. We have people who are experts in nanofab, is electron beam lithography. If you want to make a perfect structures on a large scale as a matter surface or for controlling your quantum emitters, you go to them. And of course, and it's not about taking credit from someone. It is still kind of your project, right? And it's adding more people on the paper just makes it stronger, because everything now is done up to the very high level.
Right.
So that's one way also of a risk mitigation, right? Because in this way, we don't risk that someone who gets stuck at one point. Okay, I can't now fabricate it. My etching recipe is not working, so it's over.
Can't do anymore.
Can't do anymore. So that's kind of preventing that. Of course, there are still situations where something is not working, and then we just sit down and we learn from it. Okay, it's not working because the material is way too lossy, for example. But then you start thinking, what can you do with that?
Right.
Because in some cases in optics, for example, loss is not bad.
Right.
You can do a really broadband light absorber. If you want to absorb a lot of light from sunlight as much as possible, you have to design highly absorbing structures. So there are ways where you can turn loss into gain.
Right.
And that's also kind of a risk mitigation strategy. The fact that we work with so many different materials in the group also helps. We try one, and if it's not working, and we try the other one.
Yep.
But I think really the key is that we are trying to run this as a big team, and we want every student to feel that he or she is not alone.
Right.
That there's always help. If someone really wants to develop something on his own, we say, okay, but, give yourself time or deadline. Like if you're not there in 3-4 weeks,
right,
let's discuss, let's get help. If you can't make it, let's go to our collaborators to another university. Let's do it with them,
right.
Bring it home and learn.
So you talked earlier about the mentors and the people that were in your life that helped you along. How do you view your responsibility to mentor your students, and what does that look like?
Well, I am so grateful, ever grateful to all my mentors. And I have to say, again, that I was so lucky to have amazing advisors along the way, starting from my physics teacher, and then my advisors at the Lebedev Institute in Moscow, who helped me also to go for my PhD, and my people in Denmark, my advisor in Denmark, and people here at Purdue. It's a tremendous responsibility that I feel.
Okay.
It's my biggest task is to mentor students. As I said, I feel that it's the biggest part of my job as a professor, to make sure that I help them to grow. And that's not only just helping them technically. Actually, the technical part, I would say, is the easiest because they're so smart. They do it on their own. And I learn from them, And as I said, we give them topic and we say, explain to us.
Yeah.
They explain it. So encouraging them, giving ideas to work on, and then discussing and brainstorming, that's part of like mentoring on a scientific level.
Yeah.
What we're also trying to do is to prepare them for next steps.
Right.
And giving the students the opportunity, well, obviously writing papers, that's what they all do, but also writing proposals. So all postdocs or students coming out of our team, they know how to apply for funding because they are always part of writing proposals.
Yep.
So whatever whether they end up in the national lab or university, they know how to package their ideas and to apply for funding, and that's very, very important.
Absolutely.
So obviously, scientific communication and proposal writing is also part of our job. I also have to say, and sometimes we kind of jokingly say that I'm a mom of the team. I do care a lot about the work-life balance as well for students because I recently heard somewhere that people say it's hardest for graduate students. Undergrads, they are studying a lot, but they also have a lot of fun.
Right. Yeah.
They have their support team. They have an enormous network of their fellow undergrads. For graduate students and for postdocs, they can experience much more of the isolation. And especially if something is not working in the lab, they close up. And it's, even though we try to run our team as like extended family and sharing things, and it still happens that we have to keep an eye on students and talk to them and make sure everyone is happy with how things are. And sometimes progress is slow. Yeah. So again, as a mentor, I really have to make sure that every student have this feel-good experience. Even if the project is very challenging, there are no papers for 2 years. What can we do, being maybe a co-author or having a little conference here that actually boost the self-esteem and confidence that we can do it? Being a role model for me is very important. And now I'm talking also about not students in my team, but kind of a broader reach. I know how difficult it can be for girls in STEM. And I'm aware of this issue because I had my own role models. Right. And I'm so grateful to these female professors that I met early in my career. And I always mention that. And I owe them the way I turned out and where I am now. Right. And I just... I have to. Yeah. I just have to be a role model for the girls and support them.
Well, they say, like, if you can't see yourself, meaning if you can't see a woman succeeding, then you don't know that it's possible for you. But when you see people succeeding, whether that's people of color, women, when you see someone like you succeeding at a high level, you think to yourself, okay, I can do that too. So I think there's still quite a ways to go with women in STEM. Would you agree with that?
Oh, yes, absolutely. Absolutely. And I still see that, girls and boys are different in the way they study, in the ways they behave, and just take very simple thing like asking questions. What I noticed that female researchers or students would rather ask questions after the talk, approaching the speaker.
Gotcha.
Than the boys jumping out of their seats with questions and showing them they know something. So it can be intimidating, and I've seen it all. And again, I had my own role models, and again, it's my responsibility.
Yeah. You want to be that for?
Yeah, I want to be one. Yeah. And I always encourage all my students, also in my classes, to reach out. And I love participating in outreach activities. If someone wants to ask me some questions or about career path, I'm always happy to share.
You talk about work-life balance. What do you do, like in your free time, to maintain that work-life balance and actually like see your kids and just have a life?
Oh, yeah. Oh, that's a good question.
Is this the hardest question?
Well, I have to say that, again, it comes down to luck, and I am really blessed that I had enormous support from my family and my networks throughout the years. So starting from my grad studies, and I got Victoria when I was a graduate student, so it was kind of, I was relying on the help, and my parents were back in Russia, so I really could use the support of the family, and I'm blessed that I had the support. Now with Alice and Michelle, born of course here at Purdue, we are blessed to have my parents actually who joined us. They decided to move from Russia to the U.S. and they live in West Lafayette and they help us every day.
Oh, that's great.
I simply don't know how we would, deal without them. Now, for me, the work-life balance answer would be rather different from others because, as you know, Vlad and I, we work together.
Right.
So it can be a blessing and a curse.
Yeah.
According to our kids, it's like, oh, we always talk about work. I don't feel that way. I don't feel that we always talk about work. But what it really helps us is, first of all, it's enormous support.
Yeah.
Because, I can complain about everything. He can help me with everything. But also the way we kind of distribute things that we do.
Right.
You do this, I do this.
Yep.
I will be faster by doing this. And so it's about building, if someone has an opportunity for that, of building the network and this safety net around. Of course, everyone needs family support. That's an important thing.
Yeah.
Having a partner who is understanding and you can both be successful. It just, requires the commitment and kind of a smart division of things.
So what do you and Vlad do to decompress?
Travel.
Yeah.
We love traveling. We love just, driving early Saturday morning to Chicago.
Yeah.
And going somewhere to a museum or show, go out, eat at a restaurant, and come back.
Yeah.
Recently I read this article about how to slow down time. And it's about decompressing. Time flies so fast when you're like overloaded and you don't notice like it. So one of the things that we are kind of losing a little bit nowadays in the modern hectic society is the way we stay focused and the way we slow down time. And actually traveling or getting out of the comfort zone or changing scenery is something that can slow down time. And to me, decompressing or winding down is really about slowing down time.
Yeah.
And it's easier when you get away from every day.
Yeah, when it's not right in front of you.
Yeah, because even if I, come home and I want to just, now I'm not going to think about it. And then you can't. Because there is a renovation that goes on for a year, right? And which never ends. It always has a start date, but never had the end date.
Yep.
And then, here's I'm missing the cat food, and things like that.
Yes, yeah, the every day.
Yeah. What also helps me as a busy mom is obviously I leverage all the online things that I can do.
Yes,
online.
Absolutely.
Which is super easy.
Absolutely.
Like I have, everyone is in the family is laughing that we have like deliveries every day.
Yeah.
It's because I have subscriptions, monthly.
Yeah.
So I don't have to worry about things that I always buy.
Absolutely.
So having things set up for deliveries, reminders, subscriptions, my calendar, that's something that really helps me to
not get buried.
Yeah, stay on top of things.
Yeah.
And then when the kids, grow, we just have to learn to kind of how to delegate things.
Yes.
Right? Okay, I'm not interfering right now with how the room looks like.
Pick your battles.
It's just that's your territory.
Yep.
You know, I'm not gonna fight it.
Yes.
Clean up when you clean up.
I believe me, I live that at my house as well. So
Yeah. So because otherwise you can spend the entire day, you know, fighting things,
yeah,
and, doing things. Because being having a job, a house, and pets and kids, and, you name it.
yeah,
It's overwhelming for everyone.
Right.
It doesn't matter who you are, like a professor
Yeah.
or a nurse or anyone. It's the same.
yeah,
And we all have to rely on our support
hmm
network. That's the most important.
yeah,
And delegate and keep organized.
yeah. Now, one thing I want to talk to you about is social media, because you're very active on Twitter and you have a lot of followers on Twitter. Is it something you enjoy doing? Is it something that you feel like just you need to do to attract people to what you're doing? Or
So that's an interesting thing, because I don't think that I'm active on Twitter at all. It doesn't feel that way.
Yeah.
So the reason I started Twitter is that I wanted to reach out to the audience of readers and authors when I was editor-in-chief for the journal Optical Materials Express.
Okay.
So at that time, I was defining the strategic directions for the journal, and social media was one of them. Because I said, well, you know, we want to reach out to younger people, and what are the channels? So we had to choose which social media platform would be best.
Yep.
I believe I have Facebook account, but somehow I don't use Facebook. And I don't know, so Twitter just came up like something that is maybe more suitable, because I saw other journals present there on
Right.
Twitter. So I thought Twitter would be best for me to put, you know, feature issues announcements,
Yeah.
promote new papers. And that's how I started. So I also have kind of a smaller or low-level activity Instagram account, but it's not as lively and updated as Twitter. LinkedIn is also kind of different. It's more
Yeah.
for professional networking, so I don't feel that it is really the news feed, right?
Yeah.
Again, I don't think that I have enough time for Twitter.
Right.
So I try to also to stay connected with people. And
Yeah.
as you said, when I travel, I try to post a little something just to let people know. And if I meet with someone, or also promoting new papers or new press releases.
Right.
But originally, I wanted just to reach out to younger generation, even though my daughter says that Twitter is for people who are, and then she pauses and says, "Mom, your age."
Yeah. Well, I get that too. And don't even mention Facebook to her, because then she'll be like, no, don't do that.
Don't do that. Yeah.
But I don't think like Snapchat's not necessarily appropriate for.
It's not. I mean,
Research.
it's like, what if I Snapchat about the research?
Yeah.
That would be weird.
I use your Twitter. I'm always like, where is Sasha today? Look at your Twitter and find out what exotic location you're at. And our personal goal, like as a communications department, we wanted to get as many followers for the school as you have individually. And I don't think we've gotten there yet. And I'm like, what is she doing that we're not doing? So anyway, well, thank you so much. This has been a great conversation. I really enjoyed having you here today. Thanks so much.
Thank you for inviting me. Thanks for having me.
And that wraps up this episode of Engineering Innovations. Again, a big thank you to Sasha Boltasseva for sharing her expertise, her passion, and the incredible work happening at the intersection of the physical and virtual. If you enjoyed today's episode, be sure to subscribe, rate, and leave a review. Engineering Innovations is available on YouTube, Apple Podcasts, and Spotify. And your feedback really does help us bring you more captivating conversations with faculty from Purdue University's Elmore Family School of Electrical and Computer Engineering. To stay updated on upcoming episodes and to explore more about Purdue ECE, visit our website at purdue.edu/ECE. You can also follow us on social media. We've got Facebook, we've got X, we've got Instagram, we've got LinkedIn. You can check the show notes for more information about that. And we'll be back in 1 month with another episode.